Numerical number 12. Three concentric spherical metal shells A, B and C of radii A, B, C such that A less than B less than C have surface charge densities plus sigma, minus sigma and plus sigma respectively. Find the potential of the three shells A, B and C. If the shells A and C are at the same potential, obtain the relation between the radii A and B, A, B and C. Main concept of this numerical is what? In case of a charged metallic spherical shells or a charged sphere, for a point outside the conductor, the charge appears to be concentrated at its center, and for all the points inside the spherical shell, the conductor, the potential is same. For all the points inside the conductor, the potential is same everywhere, and is equal to the potential is equal to that at a point on the surface of the shell. In this case, for all the points inside the conductor, the potential is same everywhere and is equal to that at a point on its surface. That is the main concept to solve the numerical number 12 in case of a charged metallic sphere. Now we can consider three concentric charged metallic shell. O is the common point of the three shells. This is shell C and this is metallic shell B, and we can consider another shell A which has a minimum radius, and we can draw the radius of the three concentric shells, and also can denote the charge which will be uniformly distributed over the surface of this spherical shell. In this case, QA, QB and QC are the charges which are uniformly distributed over the surface of the three concentric shells A, B and C. A, B and C. We can denote the radii of the three shells. So this is the radius of the shell A. Small a is the radius of the shell A. Then small b is the radius of the second shell B, and C is the radius of small c is the radius of the largest shell C. So again we can denote the radii of the three concentric shells. A, B and C are the radii of the three concentric shells A, B and C. So these are the three charged metallic shells which have the common center O, and according to the numerical, sigma A equal plus sigma, sigma B equal minus sigma, and sigma C equal plus sigma. So these are the surface charge densities of the three concentric shells, and we have to find VA, VB and VC. VA equal question mark, VB equal question mark, and VC equal question mark. VA is the electric potential of the shell A, VB is the potential or electric potential of the shell B, and VC is the electric potential of the shell C. So here the electric potential at the point A of the shell A is VA equal potential at the point A due to the charge QA on the surface of the shell A. Potential at A due to the charge QA, which appears to be concentrated at the center O of the shell. And also plus potential at A, due to the charge plus Q, due to the charge QB, which is uniformly distributed over the surface of the shell B, plus potential at A due to the charge QB, whereas the point A exists inside the charged metallic hollow sphere or hollow shell B, plus potential at the point A, due to the charge QC, whereas the point A exists again inside the metallic shell C, inside the charged metallic shell or charged metallic sphere, hollow sphere C. So therefore VA equal 1 by 4 pi epsilon 0 QA by A plus 1 by 4 pi epsilon 0 QB by B plus 1 by 4 pi epsilon 0 QC divided by C. For the charge QB and QC, distances will be B and C, not A. Assuming that the charge appears to be concentrated, at the center of the charged metallic sphere, sphere or shell or hollow sphere, and potential is same everywhere, potential is same for all the points inside the conductor, and is equal to that at a point on the surface of the conductor, is equal to that at a point on its surface. Therefore VA equal 1 by 4 pi epsilon 0 QA by A plus QB by B plus QC by C, whereas QA, QB and QC are the electric charges which are uniformly distributed over the surface of the metallic shells. QA, QB and QC are the electric charges on the shells A, B, C respectively. So we can draw the sphere. QA is the positive charge which is uniformly distributed over the surface, but the charge QA appears to be concentrated at the center O, though it is uniformly distributed over the surface of the shell A. Now a QA is a positive charge which is situated at the point O, and we consider a point A at a distance A. What will be the potential at the point A due to the charge QA at the point O? Though here what we can write, though the charge QA is uniformly distributed over the surface, of the metallic shell A, this charge QA appears to be concentrated at the center O of the shell, of the shell. Therefore VA will be what? In the diagram, QA is the positive charge which is uniformly distributed over the surface of the shell A, and this charge QA appears to be concentrated at the center O. And that's why electric potential at a distance A from the charge QA at the center O is V equal 1 by 4 pi epsilon 0 QA divided by small a, where small a is the distance of the point A from O, or small a is the radius of the metallic shell A. This is the potential at A due to the charge QA, which appears to be concentrated at the center O of the shell. Now plus QC is the positive charge which is uniformly distributed over the surface of the metallic shell C, and we consider a point A inside this metallic shell C, and we have to find potential at A due to the charge QC which exists on the surface of the shell. Though the point A lies inside the metallic shell C, inside the charged metallic shell C, comma, potential at a point inside the shell will be equal to the potential at every point on the surface. So potential at A will be equal to potential at C. Therefore, potential at A is VA double prime is equal to VC prime. Now, this plus QC charge is uniformly distributed over the surface, but this QC charge appears to be concentrated at the center O of the shell. That's why VA double prime is equal to 1 by 4 pi epsilon 0 QC divided by C. Though we are going to find the potential at the point A due to the charge QC, we have to divide the charge QC by the radius of the shell C, that is QC is divided by small c. A is the distance of the point A, point capital A, but C is the distance of the point C on the surface of the shell. To find the potential at the point A, that is VA double prime, we have to divide the charge QC divide the charge QC by C. That means we have to divide the charge QC by the distance of the point C from the center. Therefore, VA equal 1 by 4 pi epsilon 0 under bracket QA by A plus QB by B plus QC by C. Now, the charge of the shell A is QA, which is 4 pi A square, which is the area, into sigma A, where sigma A is the surface charge density of the shell A. QB equal 4 pi B square dot sigma B, and QC equal 4 pi C square in dot sigma. Therefore, VA equal 1 by 4 pi epsilon 0 under bracket QA by A plus QB by B plus QC divided by small c. That is the electric potential of the shell A, 1 by 4 pi epsilon 0, 4 pi A square sigma A divided by A plus 4 pi B square sigma B divided by B plus 4 pi B square sigma B divided by B plus 4 pi C square sigma C divided by C equal 1 by 4 pi epsilon 0 4 pi A sigma plus 4 pi B under bracket minus sigma plus 4 pi C into sigma, where sigma is the surface charge density, equal 4 pi sigma divided by 4 pi epsilon 0 under bracket A minus B plus C. Therefore, VA equals sigma by epsilon 0 A minus B plus C. VA equal sigma by epsilon 0 A minus B plus C. That is the electric potential of the charged metallic shell A. VA equals sigma by epsilon 0 into A minus B plus C, which is the electric potential of the shell, which is the electric potential of the charged metallic shell A, electric potential of the charged metallic shell A or metallic hollow sphere A. Now we have to find the electric potential of the shell B. Same diagram you have to consider, and in this case the electric potential at the point B on the surface of the charged metallic shell B is given by VB equal potential at the point B due to the charge QA, potential at the point B due to the charge QA plus potential at the point B due to the charge QB, due to the charge QB, plus potential at the point B. Again, we have to find the potential at the point B due to the charge QC, due to the charge QC is equal to 1 by 4 pi epsilon 0 QA by B plus 1 by 4 pi epsilon 0 QB by B plus 1 by 4 pi epsilon 0 QC divided by C. VA equal, it should be VA, VB, not VA, VB. So therefore VB equal 1 by 4 pi epsilon 0 QA by B plus QB by B plus QC divided by C, or comma VB equal 1 by 4 pi epsilon 0 4 pi A square sigma divided by B 4 pi B square under bracket minus sigma divided by B 4 pi sigma, C square plus sigma divided by C. Therefore VB equals sigma by epsilon 0 A square by B minus B plus C, A square by B minus B plus C. That is the electric potential of the shell B. This is the electric potential of the shell B. Electric potential of the charged metallic shell or sphere B. In this case, again, so if we consider the point A and B, the point A exists inside the metallic shell B. The point A exists inside the shell B. So potential at the point A, that means potential at the point A inside the shell will be equal to the potential at every point on the surface of the shell. Potential at the point A exists inside the shell B. That's why we can assume that potential at A due to the charge QA, due to the charge QA, due to the charge QB, due to the charge QB will be equal to the potential at B, will be equal to the potential at B due to the same charge which appears to be concentrated at its center O, concentrated at its center O, appears to be concentrated at its center O. Now QB is the charge which appears to be concentrated at the center O. QB is appears to be concentrated at the center O. So therefore VA triple prime will be equal to 1 by 4 pi epsilon 0 QB divided by B, because potential at any point inside a shell will be equal to the potential at every point on the surface of the shell. So to find the potential at A due to the charge QB, we have to divide the charge QB by B. And again here we can consider the diagram. We can consider the diagram, that is the point B. We have to find the potential at the point B, that is BB triple prime due to the charge QC. The potential at B, the point B exists inside, the shell C, inside the shell C. That's why the potential at B means potential at a point inside the shell C will be equal to the potential at every point on the surface of the shell. Potential at B due to the charge QC will be equal to the potential on the surface of the shell C. Therefore VB triple prime and the charge QC appears to be concentrated at the center O. So here VB triple prime, that is potential at B due to the charge QC, will be 1 by 4 pi epsilon 0 QC divided by C. So QC should be divided by C, not by B. B is the distance of the point B. Though we have to find potential at B, but we have to divide the charge QC by the distance of the point C from the center. That means QC is divided by C, not by B, to find the electric potential at B due to the charge QC. So similarly, potential potential of the shell C is Vc equal potential at C due to the charge Qa plus potential at C due to the charge Qb, then potential at C due to its own charge Qc, due to its own charge Qc. Here the charge Qc appears to be concentrated at the center O. Therefore Vc equal 1 by 4 pi epsilon 0, Qa by C plus 1 by 4 pi epsilon 0, Qb by C plus 1 by 4 pi epsilon 0, Qc divided by C. 1 by 4 pi epsilon 0 is taken common. Under bracket 4 pi a square sigma divided by C plus 4 pi b square under bracket minus sigma divided by C plus 4 pi c square plus sigma divided by C. In this case, in the second term, it should be 4 pi b square minus sigma under bracket divided by C plus 4 pi c square plus sigma divided by C. So finally we get sigma by epsilon 0 a square by C minus b square by C plus C. Therefore Vc equal sigma by epsilon 0 under bracket a square minus b square plus c square. Vc equals sigma by epsilon 0 under bracket a square minus b square plus c square whole divided by C. That is the electric potential. That is the electric potential of the shell C. Electric potential of the shell C, and that is one of the answer. Vc equals sigma by epsilon 0 under bracket a square minus b square plus c square whole divided by C. Now subdivision 2 of numerical number 12. If the shells A and C are at the same potential, comma, then Va will be equal to Vc. Or comma sigma by epsilon 0. A minus B plus C equals sigma by epsilon 0. A square minus B square divided by C plus C. A minus B plus C equal A square minus B square divided by C plus C, or comma A minus B equal A square minus B square divided by C, or comma A minus B equal A plus B into A minus B whole divided by C square, whole divided by C, not C square, and or comma 1 equal A plus B divided by C. Therefore C equal A plus B. So that is the answer. So this is the relation between the radii of the three metallic charge shells. This is the relation between the radii A, B and C, the radii A, B, C.